Okay, engineers, today we are going to see another formula for the Laplace transform. This is called the translation on S theorem. Uh, the name is also a shift on the S theorem. So what we are trying to do here is, here's the Laplace definition, the Laplace transform definition of f of t. Now, what will happen if we are trying to do the Laplace transform of the f of t times the exponential of 18? What will happen? Okay, so by definition, this will be the integral from 0 to infinite exponential minus st times here, whatever you have here goes here, so it's going to be the exponential of 18 f of t differential of t. Okay, so because we have here two exponentials, they are the same base, so that means that we can have a single exponential, the integral from 0 to infinite exponential of minus st plus at f of t differential of t. Okay, now from here I'm going to factorize the t because it's the same value, it's the same variable. So the Laplace transform of the exponential of at f of t happens to be just the integral from 0 to infinite exponential of minus, I'm going to factorize also the minus, times the s minus a and the t, f of t differential of t. Okay, now at this point we factorize the minus, so minus times s, and minus times minus, the positive. Okay, now here comes the special step. How similar is this compared to the definition? So how similar is, we have the same integral, exponential from 0 to infinite, integral, sorry. We have the same function, we have the same integral, okay? We have the same differential, alright? We have an exponential, and the only difference is here. We have the t and we have the minus. So here is just s, while here is just s minus a. So that is the only difference. The result of this is capital F of s. So if the only difference is the s, here is just s minus a, then the result of this integral is just f of s minus a, because that is the only difference. So again, here is s, so here is f of s, and here is s minus a, so here is s minus a. And this is why it is called the translation on S theorem, because it's the same transformation f of s, but here is just shift a. Okay, so the formula is the Laplace transform of the exponential of at times f of t is equal to just f of s minus a. Okay, let's see some examples, alright? Let's do this Laplace transform. What is the Laplace transform of exponential of at, then t? Okay, this is just a little example. So for example, let's say a, well, let's use generic a so that we can develop a formula. So according to this, this guy is the f of t. F of t is equal to t. So what is f of s? The f of s is the Laplace transform of f of t. In this example is the Laplace transform of t. And what is the Laplace transform of t? Is just 1 over s squared. So this is the value of f of s. Okay, so the Laplace transform of this is, according to this, is going to be f of s minus a. So if this is s, all we have to do is just to make the evaluation of s minus a. So this is f of s minus a. In this case, because s is 1 over, f of s is 1 over s squared, then this is just 1 over s minus a squared. And this is the Laplace transform of t. We can write it like this, t exponential of at. And that's it, engineers. We have the Laplace transform of this. Okay, we can From that we can develop the Laplace inverse. The Laplace inverse is going to be 1 over s minus a squared is equal to the t exponential of at. Okay? Now what you can do here, engineers, is this is the result actually. What you can do is try to place here t squared, and then if you place here t squared, then the Laplace transform of t squared is 2 over s to the power of 3, and the result is going to be s minus a to the power of 3, where 2 here and the power of 3 below. Okay, and then you will develop another formula. You will use this formula for the partial fractions when you have repeated roots. So here is the formula. Okay, now another example, and one example that we are going to use quite often. What is the Laplace transform of exponential of at sine? Well, let's try first cosine of kt. Okay, now we have to use this formula because it's an exponential times a function. In this case, this is f of t. So if that is f of t, what is f of s? The f of s is going to be the Laplace transform of the cosine is s over s squared plus a, or in this case, k squared. Alright? Now, because this is the result of this is f of s minus a, then you just replace the value of s minus a here, and you will get s minus a over s minus a squared plus k squared. And here you got another formula. The Laplace transform of the exponential times the cosine is equal to this. Now, you can develop the Laplace inverse. Likewise, the Laplace inverse of s minus a over s minus a squared plus k squared is equal to exponential of at cosine of kt. And here you can see that the s is shift, or you have a translation here in s minus a and s minus a squared here. Now, the last example we are going to cover is something very similar. The Laplace transform of exponential of at, but in this case the sine of kt. Very similar process, because this is f of t, then the f of s is equal to k over s squared plus k squared. That is the Laplace transform of the sine. Okay, because this is the result of this, according to the formula, is f of s minus a. All we have to do is just to replace here s minus a. If we do so, then we will have k over s minus a squared plus k squared. So the Laplace transform of the exponential times the sine is equal to this. Then you can have the Laplace inverse. Okay, so the Laplace inverse is going to be the Laplace inverse of k over s minus a squared plus k squared is equal to the exponential of at sine of kt. Okay? And I recommend you to keep these formulas, because you are going to use it on the homework and some of the solutions of the differential equations. Next video we are going to see an example on when to use these formulas on the Laplace inverse and how to use it. Alright? So see you in the next video.